This topic is called Moems, Micro Opto Electromechanical Systems. This is also called sometimes optical MEMS. So, MEMS is subject where you integrate mechanical and electrical components on a small wafer like silicon wafer. So, in this module, in this discussion, I am trying to bring in optical elements onto MEMS and see how we can integrate mechanical, optical and electrical elements onto the chip. We will focus more on the optical and mechanical side. So, MEMS is a technology where, as I mentioned, you can have a lot of miniaturized components on the silicon wafer. Everything started with the VLSI technology where you can integrate several of electronic components onto a small silicon wafer. And then people found that silicon is a very good material for mechanical applications also. So, that is how it started, and many components like the elements like mechanical elements, starting with the cantilever beams, diaphragms, and up to sophisticated components like motors have been fabricated onto the silicon wafer. This is a slide I have taken from the Colorado University website in collaboration with DARPA. About 20 years ago, this technology has started growing, and this Venn diagram shows the definition for Moems. So, it can be said to be a combination of electrical, mechanical and optical components in a miniaturized form. And let us go ahead, and then as we go along I will describe many other things. So, this is one of the dramatic developments by the end of last century. In one of the IEEE papers, this particular device has been demonstrated called micro optical bench. Micro optical bench. On the left hand side you see a conventional optical bench containing lenses, mirrors, prisms, laser beam splitters and all the conventional optical elements that you find in a physics lab. As you know, this is typically of the order of a few meters, and you can reconfigure all these elements. You can arrange them such that to achieve a function like an interferometer or a holographic recording system or whatnot. So, in this particular example, in this particular paper, people have demonstrated on a small silicon wafer of the size of a millimeter all the elements that we usually found on the conventional optical bench. So, you see that there are mirrors, there are Fresnel lenses, there are many other components onto the silicon wafer. They could be actuated by several means. You can raise the component up or make it lie flat based on the voltage that you apply to this. So, that the process is called the actuation, and you can configure these such that you can achieve such a certain function. So, the major difference is that this is very small and this could be made on a silicon wafer. So, there are, as I will show you in the next few slides, there are people have made several components onto a small wafer. So, other advantages that you can obtain from such a approach can be the compactness, then you have very small size, and by proper packaging all the alignment problems could be handled. You can control, in particular you can say that you can control the elements the way you want, electrically rather than mechanically or by manually, and they could be more rugged. These are all the advantages. This is one of the dramatic examples of optical MEMS devices. So, these are all the various components that you can think of that people have found on the silicon wafer. So, there are two broad categories of applications, one for power applications, one for the networking applications. Power application, typically I have given an example of a what is called a variable optical modulator. So, you can control the amplitude of light emanating out of this module. You can also switch depending on the requirement, and on the left side you have all the elements which will be useful for networking applications. For example, if there are if the elements are dependent on the wavelength, you can switch between different elements. You can provide protection in the network. For example, I will just give an example of network protection. You have a optical network consisting of a 4 elements like this configured in the form of a ring, and typically there are 2 or 4 optical fibers connecting them, where one of the first ring will take the signal in the clockwise direction and the other in the backward anti-clockwise direction, and you can configure all these elements and exchange information across them. So, if any of the links is faulty or any of the nodes is faulty, you can reroute the signals by using these optical switches and MEMS elements. That is an important application of optical MEMS. You observe that the first one is a 1/2 optical switch. There is a mirror here, and there are 3 optical fibers aligned. These two are aligned straight, and this is perpendicular to that. This is a small micro mirror which could be actuated into this path of the light beam. Suppose if a light beam is coming from this fiber entering into this fiber in normal course, when you insert this mirror, the light could be deflected 90 degrees into this. So, you can have 1/2 optical switching by using this mechanism. Of course, this is actuated electrically. So, there is an electrical signal which will push this into this. Then this is an example of an add drop multiplexer, where you can drop the signal if a fiber is bringing in the fiber in the signal. So, at this point you can drop a part of the signal, or you can add another signal into the path of the light beam. So, you can, this is called an add drop multiplexer. The third example is of an optical switch matrix, where you have hundreds of elements which are micro mirrors. Light could be deflected using these micro mirrors. So, these mirrors could be actuated to lie either flat or pop up, and in the earlier example in the previous module what I showed with the electro-optic switches, you can launch light through this fiber onto this mirror and deflect it into some port like this. So, you can configure a switch matrix. You can configure a switch matrix to route the signals from some of the input ports to some of the output ports using this switch. These are various categories, 2 broad categories of optical MEMS devices. There are many other applications that we may see as we go along. So, this slide shows the various components that have been fabricated. By the way, all these are fabricated devices from the journal literature. You may please look at the literature given at the end in the notes to get the more information about all these elements. So, the various components that have been made on a MEMS or micro optical bench are like this. There are mirrors, there are beam splitters, there are lenses, there are comb drives and so on. So, these 2 are actuators to move these elements, and there are several systems like the micro mirror arrays for routing applications and so on. These are the various components and systems that have been fabricated on a micro optical bench. So, I would like to just give you a brief idea about how such MEMS devices could be fabricated just by 2 examples. This is not a discussion for going to details about the fabrication, but just to give you an idea, we think of this particular method called the bulk micromachining. This technique I am describing is called the bulk micromachining, where the silicon wafer itself is used and its properties to achieve this function. So, just to give an idea, this is a cross section. What you are seeing is a cross section of the device. Let us focus on this device. You have a cross section of a device. Maybe if you would like to make a 3D picture, you can say it is something like this, where in one portion you have, say I will cut it at this point. So, in one portion you have this waveguide, I will draw a thin waveguide. There is a waveguide terminating at this point, there is another waveguide on this, and the region below this is etched out. Let me say here. So, this is etched out here, so that this portion is removed. So, this is a floating beam as shown here. So, the two beams are fixed to the end, but they are flexible to move around like this. So, by applying forces or other mechanisms, you can move this. For example, you can put a force on top of this and move this down. So, the idea here is, let us say this greenish region is the waveguide ring region. When the light is launched into this region and captured at the output end, based on the gap, the amount of light that goes from the input portion to the output portion varies, and if there is any misalignment between them, the amount of power that comes out reduces. So, we can calibrate this device as a force sensor, force on one axis and the amount of light output on the other axis, and you can measure what is the amount of force of the orders of a few micronewtons to a few millinewtons. So, based on the design you can achieve. This is the functionality of this device. Say you can call it as a force sensor, and you have an optical waveguide fabricated and there is a gap. That is the main feature of this. If you want to achieve this, if you want to fabricate this device, how do we go about, what are the steps involved is what I was describing in this particular slide. You start with a double coated oxide coated silicon wafer. You have a silicon here and oxide on both sides. You can also decide what is the thickness of the oxide that you may want to have, but you can coat additional layers like the reddish one that I am showing here, oxynitride, to change the properties of this waveguiding element. As we have seen, by using the effective index, you can load the waveguide and change the refractive index. So, as a first step, you etch out a small diaphragm or a slot below. For example, if this is the bottom portion, you may would like to have to etch out a region like this bottom. That is what is shown here, and not so much. We would like to etch out would like to retain this region, and maybe I would say etch out this region, and then you coat an oxide layer for waveguiding purposes, then an oxynitride layer on top of it, and then in the next step we would like to deep etch out this region. So, you make an aluminum mask, and using several etchants are there for oxides and silicon, you can deep etch this. This is called a deep etching. The RIE stands for reactive ion etching. So, the important feature of this bulk micromachining process is the silicon itself is used. The mechanical properties of silicon will be important, and typical dimensions of the orders of a few microns for the beam. This can be called as a cantilever beam. The beam thickness of the orders of a few microns, say 20 microns. Waveguides, as you know, are of the orders of a micron. Sometimes on silicon wafer they are of the orders of a fraction of a micron, of the orders of micrometers, and so on. So, typical force ranges and pressure ranges that we can talk about are of the orders of a millinewton to micronewton. So, this is an example of what can be called as a bulk micromachining process for making optical MEMS devices. I will take one more method of fabrication, more sophisticated method of fabricating Moems, called surface micromachining. So, in this particular method, once again you use silicon as the base, but the structures are made of polysilicon. The structures are made of polysilicon. So, polysilicon could be patterned such that you can have a beam and so on. You once again start with a silicon wafer, coat with nitride to adhere to the base, and then use oxide. This reddish region is the oxide, silicon dioxide, which is used as a sacrificial layer. To hold this poly layer on top of that, you put another layer of deposit and pattern a layer of polysilicon on top of this, whatever shape you want, and then etch out this oxide layer. So, this is a typical, in a very crude way, this is the surface micromachining process. So, it uses repeatedly the coating of a oxide layer and depositing in pattern several times depending on the structure. In this particular case, we are showing only a polysilicon cantilever beam made by surface micromachining process. So, you can make optical devices on top of this and then control their properties by deflecting these beams by, you can use electrodes and electrical forces between the polysilicon layer and the base silicon wafer, so that they can deflect. So, I am just using this to illustrate surface micromachining process. So, now we see what can be called as Moems devices combined with integrated optics. So, earlier whatever I have shown are bulk devices controlled by bulk MEMS devices, bulk optical MEMS devices controlled by electrical signals and other ways. Here we would like to see how waveguide based optical elements could be controlled by using the MEMS structures. So, we have at our disposal the intensity of the light, the phase of the light, the polarization, the direction of propagation and so on and so forth, that can be controlled by MEMS structures. So, this is an example of a pressure sensor where you have, this is the configuration of the device. You have the top view containing an MZI, Mag-Zehnder interferometer. This is an MZI. I am just illustrating the principle, not finer details, but some technological issues also I will highlight later on. So, you have a Mag-Zehnder interferometer as a top view, and just below the arm of the one arm of the Mag-Zehnder interferometer, I etch out a diaphragm. So, the configuration of diaphragm is as shown here. So, from the top we do not visibly see anything, but etch out from bottom. So, you can assume that this is lying on the diaphragm. So, a typical diaphragm is like this. Typical thickness including consisting of the waveguide etc., could be of the orders of a few microns, 20 microns, and waveguide dimensions, as you know, in silicon will be of the orders of a fraction of micron or half a micron. Typical dimension is 0.5 micron by 0.22 micron. These are typical dimension of an optical waveguide. And large refractive indices, that is another important property of silicon, of the orders of 3.4 refractive index. Oxides, of course, you can oxidize the silicon and you have of the orders of 1.49 or so. So, these are typical parameters of the silicon photonic devices. So, this particular structure has multi layers, layer of oxide, layer of nitride, layer of oxide, and light could be guided in this higher refractive index. Nitride is much higher the refractive index than oxide, light could be guided in this region. And this patterned structure of the channel waveguide is effectively for confining the mode in this region by effective refractive index. So, when you apply pressure uniformly on this top of this interferometer, so the stress induced refractive index change is larger here. The other arm of the interferometer is not affected much, and there is variation of refractive index in this region alone, in the diaphragm region, in particular on the waveguide region, and so there is a different phase shift. There is a different phase variation between these two waveguides, which can be measured as a phase shift output at the end of the interferometer, which is converted into intensity change. So, the intensity output is dependent on the phase change at this point, typically cos square delta phi, like in other MZI structures. So, you can calibrate this device for pressure as a function of the light intensity output. Light intensity output with the pressure, typically I will show a few pictures later on. So, this is a example where we use MEMS. Diaphragm is a MEMS device. Diaphragm is the mechanical device which is used to control the optical properties of the light propagating inside this waveguide. We have combined the integrated optics plus diaphragm for an application to pressure sensing. I will show you few more details in the next few slides. So, if you want to study such optical MEMS devices, guided wave optical MEMS devices, we have to deal with the mechanical equations, the optical equations, and if there are any electrical effects, electrical equations all combined into a single unit. So, first you solve the mechanical equations of the diaphragm, then from the solution you get the stress variations induced, as we have seen in the case of acousto-optic effect. In this particular case we are using what is called the elasto-optic effect, and you get the stresses involved. Then you can relate these elasto-optic effects to the refractive index variations of the waveguide, and you can choose a proper optical configuration like the Maxent interferometer. In that particular case, read the output as a function of input signals. This is the broad methodology. I will show a few equations to illustrate how this is being done in the case of the pressure sensor. So, this is a typical case. You can look at the current literature for more details. You have a mechanical equation of motion. So, on the right hand side you have the pressure, this is the motion for the diaphragm, and you have been given several boundary conditions to determine the displacement function of the diaphragm, and also of course we can relate it to the stress variations of the diaphragm. So, the stress variations typically are derivatives of stress could be stress variations could be considered as derivatives of displacement. Another important feature that is illustrated by this is the stress variations are a tensorial in nature, even though you have uniform pressure or scalar values of the pressures based on the diaphragm. The resulting induced optical changes as well as the mechanical changes could be vectorial or tensorial in nature. So, the idea here in this particular slide is to solve the mechanical equation and obtain the displacement functions and the stress variations. So, the stress variations could be reflected to the optical properties. So, using optomechanical coupling expressions you can relate the refractive index variations with the stress variations. So, stress variations I am showing you as variables, different values in different directions with different coefficients, and they are also different for different modes, TE and TM modes of the light propagation. The waveguides will have different coefficients. You can say that the C2s are different, for example C2 dash and C1 dash and C2 dash, C1 dash and C2 dash, and you have refractive index variations also variable along with the stress. So, delta n is dependent on the is a function of the stress. That is an important feature of these elasto-optic devices. Finally, of course, we can define the sensitivity of the sensor as a phase shift with the input perturbation. For example, in this particular case, perturbation could be the pressure which is resulting in the change in the phase. So, you can refer to the current literature for more exact relationship between the delta n and the stress induced changes, which is different for different types of materials like silicon. Even in silicon it may depend on the doping concentrations and so on. You can use to control the mechanical and optical properties, not only electrical properties, optical properties of the silicon junctions and wafer. So, once you get the mechanical analysis and put it in the coupling expressions, you need to do the optical analysis. An important feature that we noted here is delta n change, refractive index changes are a function of stress which are functions of z. So, if you have a diaphragm like this or a waveguide like this where you are experiencing the displacements, so the refractive index is varying along the z direction. That is an important feature of many of these MEMS structures. Delta n is a function of z. We have seen such analysis for tapered waveguides like branches and couplers and all those things. So, in this particular case I am showing you very simple analysis for the MZI. If you are using MZI as the optical structure, you can relate the intensity with the phase shift and phase shift with the changes in the displacement or the changes in the propagation constant due to the change in the refractive index arising due to elasto-optic effect, and you can finally calculate what are the phase shifts. The phase change due to changes in the length could be estimated and finally resulting in the sensitivity expressions. So, you can finally relate the properties with the sensitivity properties with the change in the phase as a function of change in the perturbation. So, this is a broad description of how optical MEMS devices based on optical waveguides could be analyzed. So, first we have the mechanical analysis, relate that mechanical analysis with the optical properties by using the elasto-optic effect, and then use the optical analysis to study the propagation of light in the optical waveguides as a function of the input perturbation parameters and determine all the properties, required properties. So, this is a simple plot that we have done in our lab for various values of the this shows various phase changes for different modes across different variations. So, change in the optical path length and as a function of the distance, and nowadays there are a lot of numerical analysis tools which can help us to solve this tapered waveguide like beam propagation method we have seen. There are many other new techniques that can be used to measure these to analyze these properties. Typical sensitivities are of the orders of a few microradians per Pascal, and typical ranges can go up to several megapascals. So, this chart I have shown only to just to illustrate that such an analysis could be done and be very useful. You can see the current literature for more exact description of the devices, their technologies and their functioning. So, just to highlight or to summarize, I have shown you this device which consists of a mechanical element, the diaphragm, an optical element, a magnetic interferometer based on the optical waveguides that we have studied earlier, and then interrelating them to achieve a function like the sensing. So, thank you very much for this module.